Hello physics students. Welcome to our next topic, conductors and capacitors. Now in the last topic we just finished, Gauss's law, we studied a little bit about conductors charged in equilibrium. This topic we're going to go even deeper and learn a lot of interesting things about what happens when you charge a metal and put it into a situation of static equilibrium. In other words, you charge it and then you stop influencing it. Later in the year, we'll be talking about conductors, metals, when they're not in equilibrium. Like when a battery is involved, if I connect this metal wire from one side of the battery to the battery maintains an electric field in the wire, and then we're going to see that that causes current to flow through the wire. Not the case in this topic. We dump charge onto a metal, and then it comes to equilibrium, and we're going to learn all the things that are true about the metal in such a situation. So, as I said, we learned some things already. So today, some of this is going to be review. We're going to be refreshing and then adding today. So, charge conducting spheres, 1. In static equilibrium, when there's no battery, and that means no electric current, the following things are true for a metal. The electric field in the metal is 0. And what I'm talking about is inside the actual place where they're metal atoms. And why is that true? Well, if there was an electric field that was not 0, like for example in this diagram, suppose like maybe I've got this in 2 parallel plates and it's causing an electric field like this, what would happen is the electrons would feel a tug to the right like this in the opposite direction electric field. In a non-metal, like a piece of styrofoam, they would just feel that tug and they wouldn't go anywhere. But in a metal, they're free to move. That's why they're called conductors, right? The metal can conduct electricity. So they migrate and they stick on this back surface over here. And they, in the process, left some protons, because atoms are made of protons in the middle with electrons orbiting. The protons can't move unless you melt the metal, and then all of a sudden the whole atom can move. But if it's a solid metal, those protons are locked, but the electrons have left here. So these are now protons that used to have partners and be neutral. So then the metal has now this sort of charge distribution, which creates its own electric field from plus to minus. And you see, it cancels the electric field. Does it always cancel the electric field? Yes. If it doesn't, let's suppose it's a little shorter like this. That means there's still a net electric field like this. More electrons come this way and more build up, and that electric field keeps growing, growing, growing until it exactly matches the original electric field. Net electric field is 0. So that's one thing you have to remember, and you probably already remember it from Gauss's law. The other thing that means is that all excess charge has to be on a surface. Of course, I don't mean all charge, because that's all protons and electrons. So in here, there are equal numbers of protons and electrons for each cubic whatever volume. So why must that be the case? Well, let's suppose I have 2 excess electrons right here. They're going to repel each other. Force, force. Again, they're in the metal and they're free to move. So they race away from each other and go to the surface. So that's always true. All excess charge has to be along the surface of the metal. The other thing that must be true, kind of related to this, or actually this, is that the electric field at the surface doesn't have to be 0. It has to be 0 inside, but at the surface it doesn't have to be 0, but it must be perpendicular to the surface of the conductor. Why? Well, let's suppose hypothetically we've got an electric field like this, not perpendicular. So there's a component of the electric field that runs along the surface like this. Once again, the metal has electrons in it which will now feel a tug in the opposite direction of the electric field. So they'll start moving this way. And they'll start accumulating over here, producing an electric field to the right. And that migration keeps going until it cancels the electric field, the original that was pointing to the right, to the left. If it doesn't cancel, more charges keep moving until it does. And then so the electric field ends up perpendicular to the surface. All right, if you need a moment, I'm going to create a pause to allow you to copy this down. Let's move on. Because of these facts about the electric field, 1 and 3, it means that the entire conductor is an equipotential. Not just the surface, but any 2 points in the middle within the metal are equal voltage. And how do we reason that out? Well, let's take two hypothetical points inside the conductor. So by the way, this is a sphere. I've drawn it, and I put positive charge on it, which means I strip some electrons off. So we've got an electric field that points outward everywhere, perpendicular, 90 degrees to the surface, as we saw here. None in here. So voltage is defined as two ways, two definitions for voltage. One is the joules per coulomb on each electron, the thrust or the energy that each electron gets moving from one point to another because of the electric field. So again, voltage is down to a single electron. This battery is 1.5 volts, whether I let one electron go from one side of the battery to the other or 1,000. So it's down to one electron, that ratio of joules per coulomb. So that's one way. The other way to define voltage is saying the same thing, integrating the electric field along the path that the charge moves. Because if there's electric field running along that path, it's going to give a thrust to those charges, a joules per coulomb. So if we use that definition, integrating electric field from here to here, the definition of voltage, and of course the dot product means the electric field has to be in the same direction. Well, if there's no electric field in here, there's no voltage difference between here. These 2 points are equal voltage or an equipotential. Okay? How about along the surface? If I integrate around here, now I have electric field here. Here I didn't, right? But along this integral path, I have electric field, so I could say maybe there's voltage there. Well, again, the voltage is the negative integral of E ds. But the dot product here, the E is not zero, but the dot product means that the vectors have to be at least partially aligned. So this is a dot product of positive when you dot these two vectors. But if you go like this, it's a little less positive. And then when you go 90 degrees, the dot product of those two vectors is zero. There's no component of this vector that lies along the displacement. So the dot product, 0, 90 degrees. So all along the surface, equipotential. Okay, so that is equipotential, the entire conductor. Okay, some other facts about maybe a conductor like this. You also need to be able to represent those ideas about the electric field and voltage in a possible graph. So let me make some room. All right, so if you need a moment to catch up, I'll create a pause to allow you to copy that down. Okay, as I said, the graphs. So the electric field. And let's suppose the conductor has a radius of capital R. Well, maybe I'll go a little bit more here, shift it over here. So at the surface, there's a certain amount of electric field. Twice the radius away, kq over r squared is the formula for electric field for spherical symmetry. Because of the r squared, twice as far away is not half the electric field, but a quarter of the electric field. So we've got this downward descending curve that's proportional to 1 over r squared. So that's outside the metal. The further you go out, the weaker the electric field gets. Inside the metal, the electric field is 0, so we would have E equals 0 here. Okay, so that's a graph of the electric field. How about the voltage, the potential of, and remember, delta V is the voltage between any 2 points. V, without a delta, means still the voltage difference between 2 points, but one of the points is infinity, deep outer space, okay? So when I say V, it's the electric field integrated from outer space inward. So when you're all the way in outer space integrating, there's almost no electric field, so you have almost no voltage. But as you're coming in to the surface, you accumulate more and more electric field as you're integrating against the electric field. You're getting more and more positive voltage because you're going uphill of the electric field. You're like lifting the charge against the electric field where it wants to go. And then some people make this mistake. They say, okay, integrating, and then once you go here, because there's no electric field, the voltage drops to 0. No. When I say what's the voltage at this point, V, not delta V, I'm saying what's the electric field integrated from infinity to that point. And so the integral stops here because there's no more electric field. But the voltage I've accumulated coming in is still there. So it just that the voltage stays constant the rest of the way in. And this would be like maybe K, Q of the sphere over R of the sphere. So a couple graphs. Okay, so that's one thing you have to be able to generate, just those concepts of graphs. Maybe we could have shells within shells and do all kinds of stuff with graphs, but I just want to touch some of the brief ideas here. Another thing that comes up sometimes in a topic like this is a utilization of this idea. And a problem that uses that idea could be like the following. Let's suppose I have two metals. Okay, these are not metals. But let's suppose they're two spheres, different sizes of metal. Solid, hollow, doesn't matter. One of the spheres, I put charge on it. Okay? The other one's neutral. What I do then is I connect these with a long wire, like this. And I say, what's the charge now? Some of this charge is going to go to the other sphere. Because again, charges want to repel each other like charges. So if this is like negative, for example, the electrons want to fly away. So some of them are going to go to this sphere, but not all of them. Because then they're concentrated here and they want to go. So there's going to be some kind of balance that occurs between these two in terms of charge. Okay? How much charge is on this one? How much is on that one? How do we calculate that? What we have to realize is that when I connect these with a wire, you could now think of this as one metal, one conductor, not two, but one with a skinny part in the middle. And this has to be an equipotential. In other words, the voltage of this has to equal the voltage of this. And so that's what balances out. The voltages balance out. Okay, so we can use that to figure out the charges that are then on the sphere after equilibrium is established. So let's say we've got plus 24 microcoulombs on a 0.1 meter metal sphere. So that's the situation. Sphere connected to uncharged sphere. As I said, the charge moves around until, very rapidly, until an equipotential situation is achieved. In other words, the V1 will equal V2. Okay? All right. If you need a moment to catch up, I'll create a pause to allow you to copy this down. Okay, so moving on. What is the voltage? Oops, missed a spot. There we go. The voltage of sphere 1, it's K Q1 over R1. We don't know what charge it is. Some of the charge is over here, so maybe it's like 12 or 8 micro. We don't know. The voltage of the other sphere. Now I could do this. But what I'm going to do is instead, now I have two unknowns. I'm going to do this. Q1, unknown, over this radius. Oops. Instead of saying Q2, I'm going to say 24 microcoulombs minus Q1. Right? In other words, if 10 is over here, 14 is over here. Because charge is conserved, and if we had 10 and 14, charge would be conserved. We'd have just as much as we started with, which is 24. So that's what this is saying mathematically. What I could do is multiply both sides by 0.2, giving me 2Q1, 24, add Q1 to both sides, I get 3Q1. Oops. Divide by 3, and I get positive 8 microcoulombs on sphere 1. Sphere 2 is 24 microcoulombs minus 8 that's on the first sphere. And so that gives me 16. Okay. If you need a moment, I'll create a pause to allow you to copy that down. All right, so that's our first little study of conductors in static equilibrium. Remember those facts. Get them nice and firm in your mind. The electric field is inside the solid part of a metal, is zero inside the solid. The electric field is always perpendicular to any surface of a metal, so it cannot go like this. It's got to go straight out from the metal. All excess charge has to be on the surface of the metal. You can't have two electrons inside of a metal. They're going to race apart to the surface. And finally, that means that every point on the metal, any 2 points are equal voltage. The entire metal is an equipotential. Okay? And we did a little graphical sketch of those ideas and a little quantitative example. All right, so that's our first video. I will see you in the next physics video.